All right, let's get started. Good morning. This is the last lecture before spring break. I mentioned last time, just a reminder, that right after spring break, there will be, as usual, a homework due on the Tuesday after. So, come to office hours today, start early. It's going to be all the way up to 5.2, which we will talk about a lot today. But I'll, of course, try to cover this as well. I will also see if I have time to talk a little bit about the programming assignment that I know is not due until the 15th. But I'm thinking maybe some of you want to get started over the spring break, and you will be able to after this lecture. You'll learn a little bit about differential equations. I will not review 4.9 for now, just saying that we finished up integration by talking about these infinite things, either functions going to infinity or the integration intervals going to infinity. There were some tricks. They are kind of special, but it's kind of nice. And you have some exercises on it. I think it's going to be fairly straightforward. So those, go ahead and do those exercises. I don't think I assigned anything too tricky. I did mention, though, that there is one exercise, 6 and follow-up 9 in that chapter, in that section, that need some more work. And I posted a function on the web page called Laguerre Quad that will give you the nodes and the weights that you need for problem 9. So for 499, that function will help. For 496, it's just a proof that it's fairly similar to what we've done previously. Then I said that the big thing that's going to happen now is differential equation. And it's not just a big thing in this course. It's a big thing everywhere. This is really an important part of numerical analysis. And in one way, it looks like quadrature. You're integrating something. In fact, the model problem we'll be solving all the time is y prime equals f of t comma y, where this is essentially anything, but we'll talk about how much anything it is. But if you think about it, if there was no y here, it would just be integration. So in principle, you could use, Simpson's method for this if there wasn't a y there. Now there is a y, which makes things connected. So that's the issue that's going to happen. And we'll look at different methods for that. We'll, in this section, or this whole course, we'll just be talking about initial value problems. So you start at some point. So typically, you're given a value at the left endpoint of your interval. And I think the notation they use is that they call that number alpha. And of course, then you want to integrate. We often use the term forward in time. So we say that we know what it is at time t, and we want to predict it for any time, but going only up to time b. Okay? So just for the big setting here, in terms of existence and looking at Lipschitz continuity and things like that, the times are usually a fixed interval. It's almost never interesting to look backwards in time. Some solutions don't, they blow up. They don't have, it's not relevant. You don't have to look backwards in time. That's a good thing about an initial value problem. Typically, you have a finite value. And we want to be able to have theorems that tell you can go anywhere you want, but typically, you don't need to be able to say that you go all the way to infinity. This is the real problem. If you want to think about something, of course, almost anything in physics and engineering and science where you predict something can be modeled by differential equations. It might be that it's partial differential equations, but when you hear the word simulation, it's to a large extent the idea of solving differential equations. So whatever you wish, predicting the oscillations of a bridge that they haven't built yet, etc. Right? It's going to be some sort of dynamic problem like this. You start at the time A, and you may be integrating time under certain conditions, and you want to predict what happened at time B. Is the bridge going to break or not? That would be a partial differential equation, but it's the same idea. You would be using these methods anyway. So that's what we're doing. We had some theory last time. Let me quickly review it. This is, as I said, much from Math 1, 2, 3. We don't need to know much of that at all. That is in no way a prerequisite for this course. But since we're going to throw out a proof of a method, we're actually going to need to know a few things. If you want to prove, we're actually going to do something quite remarkable. We're going to take Euler's method, which is the simplest possible that you know before, and prove that it converges. That's pretty strict. We're going to be able to say that the smaller you make the step size, and we'll put a bound on it. And maybe you're not surprised because we did this already for everything else we've done. But here it's harder because there is this iterative recursion effect where we're going to keep on stepping. And it's much more difficult. It's quite remarkable that we can come up with a proof here. Now, in order to prove that a method works for an equation like this, certainly we need to know at least that there is, so let's see, convergence we're going to define more carefully, but I think you all know. It's that you're getting closer to the true answer, right? And previously, we never questioned the word true answer. But now, there are issues. Differential equations are iffy. There can be many true answers. There can be no true answer. So we need a little bit of theory just to be able to say that we want existence and uniqueness before we start talking about that we're getting the true answer eventually, right? So that's basically the extent that this theory goes. We started off with the important concept of Lipschitz continuity. I said that this definition goes right at the differential equation, where the issue is in the y. So this theorem talked about Lipschitz continuity or Lipschitz condition in the variable y. I did it on the blackboard where I just said, let's start by Lipschitz without f of t comma y. Just a function of one independent variable. You can define Lipschitz continuity exactly by this here. Namely, let me write it up again, that if you have a function, the jump, you're making a jump on the independent variable, okay? And you want to be able to say that the corresponding jump in the function value is bounded by a constant times that, okay? And that constant is called the Lipschitz constant. And we talked about what it means, and I said it's something in between differentiability and continuity, in the sense that it certainly implies continuity. If x is, let's say, equal to y, I mean, if it goes closer and closer, no matter what this is, these values are going to get closer to each other. So this does not allow for a jump. Okay, so continuity certainly follows from this. It is stricter than that, and we had some examples of that. And I guess the typical example for that, we had various arguments, but one is f of x equals, well, you could actually just do square root starting at 0, but I think we did this. So we did 0 and then square root of x, right? And you can try to convince yourself that this is not working out. By various arguments. You can just think about it, that if you're standing at 0 here, and you're making a little jump in x and y, so let's say, just to see that, why don't we set y equals to 0? And x could be x, but let's call it epsilon just to show you guys that I want it to be really, really small. Okay? Then clearly what we have here is f of x is square root of epsilon minus square root of 0. Okay? You want to bound by epsilon minus 0, right? So basically, you're saying that square root of epsilon is bounded by epsilon times a constant. Well, if epsilon is going to be really small, that's not going to work, right? How are you going to set L? Try L. Try 1 million. Well, whatever L you give me, I can give you an epsilon such that it's not enough, right? Just divide it down. So it's not working out. Basically, intuitively, what it's saying is that it has to be a linear relationship here. Someone pointed out after lecture last time that this is actually, let's see, stronger than uniform continuity. Because uniform continuity would allow for, it's very related that you want to be able to bound something, but it doesn't insist on this being linear. So this particular relationship here, for example, that you say that this constant here is allowed to depend on this epsilon, basically. Okay? So for uniform continuity, that would be, of course, implied from this, but it could be a little weaker. So this function would be uniformly continuous, but Lipschitz puts a little bit stronger requirement on it. However, uniform cannot depend on where you are. The position, the actual x value, just to gap the epsilon. So that's how you think about that. This would not be Lipschitz. Let's talk about differentiability. Differentiability kind of tells you that there's a slope here. And in particular, if you have, it's kind of easy to see here that if you tell me that your function is differentiable and you have a bounded slopes, bounded derivatives, it's clear that the largest derivative you get is a good selection for this L. Because it can never be worse, right? So draw a function like this, try to pick, say that it's differentiable everywhere and it has a maximum derivative. You cannot pick 2 points such that the gap is, because that would mean that it had that largest derivative everywhere. And everything else would make it easier. So differentiability implies this, technically speaking, someone asked about x squared. There is this issue with if the derivative is not bounded, which, so either, I guess when I said that I meant that either you have a bounded differentiability, it implies this. Or you could say that globally continuous. You know, I like to cut off the domains. When we do these examples, typically we'd like to cut off the domain. Because a simple function like x squared, like I talked about last time, would not be, it's of course not Lipschitz continuous on all of R, right? Because well, you can think about the derivative. It goes to infinity, right? You cannot give me one single value of L. If you give me an L, I could always go so far to the right. Remember, the derivative is 2 times x, right? Such that I have a higher derivative than that, and then I can violate your condition for any L you give me. So yeah, that's what would be called globally Lipschitz continuous. But as soon as I bound it, if I say that x, no, you're just allowed to go between minus and plus minus 1 million, right? Then you can, all these nice functions, differentiability would imply that you can find a Lipschitz constant. So that's what's going on here. We have these conditions. Why do we talk about this? It's the right condition for ODs. Okay? It turns out to be for different things in calculus, you need different conditions, but we don't need differentiability. Having said that, everything we do is going to be differentiable, because the methods we use are based on Taylor's method, and we actually need more than differentiability. But for the theory, it's nice to know that we don't quite need it to be differentiable. And an example of a function that was not differentiable, but is Lipschitz, is something with a kink. And the simplest possible is, of course, the absolute value of x. So you cannot define a derivative at 0. But of course, the function can't run away too far if you make a little step on the independent variable. So that's a good example. So that's all you need, actually. You don't need differentiability to define these things. And you'd also see in a nice way today when we prove Euler's method's convergence that we're not going to assume any differentiability. Well, yeah, so there comes the little problem that we have the fact that we're going to do Taylor on things. But for the actual step of adding things up, you'll see that we'll use exactly this condition. We need to say at some point that if you plug in two different values, we're going to make errors, basically. And those errors, we don't want them to be multiplied by too much when plugged into the function value. That's basically what's going to happen. So anyway, don't be confused. I know people asked yesterday or Tuesday, but how does that relate to that? Why am I now calling it y? It's exactly the same thing. The difference is that here, I call it x and y. Here they call it y1 and y2. And there they added a dummy variable t. It's not a dummy variable later, but in terms of Lipschitz condition, t has nothing to do with it. So that is really the same as that. Anyway, here's what I mentioned. If you do have the derivative defined, and you can bound it, so the derivative is never greater than a value L, then of course it implies Lipschitz with that value. That's probably for your homework. I don't remember exactly your homework, but that might be the easiest way to find a Lipschitz constant. Okay? But don't use that to find the Lipschitz constant for this, because you would violate the theorem, right? Because this is not differentiable. But if I give you a function that is differentiable everywhere, and you can use that theorem. Of course, finding a Lipschitz constant for this is easy. It's just a little bit of very easy algebra. Or just looking at it, you can see that 1 works fine. But not less, because it's kind of x, right? So if x and y are both positive, you need 1. But you don't need more. Here comes the main theorem, saying that this is exactly what you need. And by that, I mean you get existence and uniqueness if f satisfies this. OK? So looking at the details here, I mentioned before, the domain is really the time interval you're looking at. So the time you kind of don't have to worry about, but you can imagine an f here. I think I make an example today where you can have something, if time goes to infinity, it can blow up. It's fine. Because you just need to show that you're going to a certain point B. It's just not relevant. We don't necessarily, it could be relevant to say that, oh, I know the solution exists for any time you want to, you can let time go to infinity without the solution going to infinity. Sometimes it might make sense to ask that. But normally you know where you're going. And this strip here, I call this a strip because we're looking at the ty plane, and we're just looking at a strip of t values. But in this formulation, we want all of the y values. And that's a big problem many times. So for example, if I give you y square, I mean, this x square here we said was not globally Lipschitz. So a very simple equation that you solved probably in Math 1b was this guy here equals to y square. Okay? And you would immediately say that, wow, that doesn't really satisfy this condition. Is that just a technicality? Or is the theorem not broad enough to cover that? No, it's completely real. Because if you put y square here, it seems like a small modification compared to the model problem where you just have y, and the solution is an exponential. Now, y square here, and it blows up, explodes to infinity at a finite time. Okay? And it doesn't mean that the solution doesn't exist, but it certainly means that you cannot give me a b, whatever you want, and I can say that it exists, because it blows up. In particular, y prime equals y square, starting at, I think, y0. Had the solution y of t, what was it? 1 over y0 minus t, right? Well, I have it in my notes. I think this is it. So it starts at y0, and at a time 1 over y0, it blew up, right? So is that good? I mean, this could be the real solution, and everything is fine. And in fact, you could, if you want to use a theorem that tells you that the solution exists up till that point, you can actually do that. But this theorem doesn't work, because it insists that you find a Lipschitz constant for all of. What you have to do then is to start messing with this value here and say, if I promise that y is not going to be more than this and less than that, then I can find a Lipschitz constant. And then this theorem, a different theorem would guarantee. So this is you can specialize this. It's not the main purpose here. I'm just trying to give you an indication about the issue with things going to infinity and globally Lipschitz, and that you might have to cut things off. But it's a very nice theorem. It tells you that, if you have this, which we very often have, Lipschitz continuous f, then you can start talking about the solution. And it's clear what you mean, because uniqueness means that there is one and only one solution. I did mention this briefly. This is more for numerical analysis, but it's something that is discussed in 123 as well, even if it's not numerical analysis, namely well-postedness. The idea is that if you make errors, how bad is it? Right? And we're always going to make errors. And you want some study. And differential equations are kind of complicated. So we want to make sure that errors don't completely ruin things. And the way this is formulated is the following. Suppose that every time you evaluate f, you make an error delta. And I promise you that the delta, these errors are kind of random, but they won't be larger than some number epsilon. So they're kind of small, but random, and they always show up. Clearly, I'm going to solve the wrong problem, and we're going to call the new solution z. OK? And also, we're not going to do this too much, but why don't you just perturb the initial condition as well? And again, by a value that is small. Right? This is how you define well-postedness. And well-postedness means then that you're getting the wrong solution, but it's not that far away from the true solution. And that's a very relative concept. We don't really care about. It's not like it's really close. It could be super far away, because there's a big constant here that I don't care about. What I do care about is the linear dependence on the epsilon there. So in other words, whatever the error is when you did this, you can have very sensitive problems that are still well-posed. Sensitive being that you do a tiny little small perturbation and things really explode, right? But if you divide epsilon by 2, it has to come twice as close. That's what this is saying. So it's more dependence on epsilon, linear dependence on epsilon. That's what well-postedness is. And again, we really want this to happen, because if you have a problem where you make a small error and things blow up, and then you keep on making their error even smaller, and it doesn't get better, or it gets better too slowly, that would be a disaster for numerical methods. So the good news is that, of course, it's Lipschitz again. Exactly the same conditions. If you have a Lipschitz condition on f, then you have a well-posed problem. So as I said before, it's exactly what we want. All right? That was just a theory, basically just introducing this uniqueness and the Lipschitz condition. Let's talk about a method. The first method you know is, of course, Euler's method. Let me put it here, so we have it next to the equation. So it's actually good. I know in Math 1b, we draw it like this, and we start at 0. Why not? I will be sloppy, and usually we try to solve this general problem. But often I will just assume that a is equal to 0. And it clearly doesn't matter. It's just a shift, right? And I apologize if I use different notation. But very often I will just say we start at 0. And I guess we call this value alpha, right? And here's the true solution, y of t. So this is the ty space, so to speak. And let's say you want to stop somewhere. So this would be your b then. And to be honest, when you call this 0 here, you usually call this big T. I might do that accidentally. No, let's not confuse too much. Kind of doesn't make sense to have a b, but not an a. Now, all right, so we know we have a nice f, and this y exists, and everything is good and happy. So numerically, we want to compute this. It's clear that you want to do something of type, the quadrature method we've done before. You want to introduce a grid. Remember, when we introduced a grid, you could evaluate things here. Just think a little stupid here about this. Why don't we just do Simpson's method? Right? We're trying to compute an integral of f. Well, I mentioned before, it depends on y. That's why. That's why you can't just use Simpson's method, because you don't know what this is. You're trying to integrate. I'm actually plotting in the wrong thought. But there is, of course, a function somewhere of, there is an f here. That is a function of t and y of t. OK? And it's actually equal to y prime. So the way I drew it is wrong. It's not negative, but that's OK. Pretend that this is that function, right? Really, what you want to compute is the integral of this f. OK? That is exactly, by the fundamental theorem of calculus, the jump from there to there. You see, we're really, so that's what I mean by you're trying to integrate this equation from a to b. And the problem, the reason it doesn't work, is that you don't know f until you know the solution y, which you're trying to compute. OK? So there are various ways to handle that. One way is to do the PD trick that you actually can do. You set up a big system of equations that you have to solve. You actually allow yourself to pretend that you know y, but then you don't, and then you get an algebraic system that you solve. But most of these initial value problems are solved by the very nature of the fact that you start at a time and you evolve it in time. So you're standing here and you're trying to predict the next value in some sort of accurate way. all methods we talk about will have this pattern. It might be that we need to solve some linear system, but really we're not going to try to talk about these values over here until we get there. Okay? So we just step by step. And there are many reasons to say that that makes sense. One is that the theory tells you that if you start an alpha here, the next solution in the future is completely given. So it just makes a lot of sense to start here and go a step, and then you say, well, now the rest of the solution is completely well specified and mathematically sound. You don't need these values to compute this solution. In fact, if you do, you're making some inconsistent, weird error. The number here by causality is not supposed to affect stuff that happened in the past. So it makes a lot of sense to start somewhere and move forward. I'm just motivating the method, the type of methods we're going to use. So these methods are, of course, going to become recursions in that sense. If you give me a value, I can give you the next, right? And then given that, you can get a next. So it's really recursion equations. And what is the simplest possible? It's Euler's method, which just takes the method and say, well, there is a slope here, and that slope is, of course, exactly equal to this value f, right? And you can compute it, because you're given the starting value alpha. So the very first thing you do is to just do f of t comma alpha, sorry, f of a or 0 comma alpha, right? And you get a slope, and that's the slope. Okay? Unfortunately, it doesn't make you much happier, because as soon as you start going, the slope changes. Unless, of course, f is a constant, when you wouldn't use numerical methods anyway. But in general, the slope will change as you start moving. So it will be wrong. And indeed, if we draw it a little bit more carefully here, it does something, right? While the slope does that. Okay, so Euler's method says, let's just pretend that didn't happen and go and keep on going in this slope. But after a while, of course, you're wrong. So you just take a finite step up until time. And we're going to call this h. That's the method. Now you say that, OK, the slope is really wrong. I should not continue here. Let's just stop and do a new slope. And there's, of course, a new slope here. What is the value of that slope? It's f evaluated at this value that we now computed, right? Or in other words, f of h comma this number. Just plug in the point. F of t comma y is defined in t comma y space. Any point here, you give me a slope, right? And again, in Math 1b, I think we even drew these direction fields, didn't they? And you were supposed to guess where the solution was based on that. I'm just giving some understanding for how an ODE works. Anyway, so at this point here, you can compute a new slope. And then, of course, this is better, so you make another step like that. But then you give up. And this is Euler's method. What's wrong here? You see things that can go really bad. There are two sources of error. I start exactly at the true solution, because that's given. And I make a step. Why am I making an error? Because I pretended it was a straight line, right? And it's not. So if it's a quadratic, there will be an error in that. What's the error here? Well, let me just say it's, of course, the same thing that it's the true if the true solution was a straight line, it would going through here, it would be perfect. But there's another source of error. I'm getting the wrong slope, because I'm already a little bit off. And you'll see this when we prove that there are these two things happening. The errors will go bad. So you take a step. You made a little error. You compute a new slope, but the true slope is something else, right? So you're setting off at the wrong slope. And these errors will add up in a very unpredictable way. Or it's predictable. We'll figure it out, but it's just not trivial. Okay? This did not happen for the quadrature. Simpson really said, you compute this, you compute this, you compute this, and we add up the errors. Here, you compute this, but unfortunately, when you compute the next one, there's an additional error because you made an error in the first one. That's what I'm trying to say. Anyway, let's write Euler's method. Here they used the notation W. So Euler's method would say that you start at a W0. So of course, pretty trivially, W0 is equal to alpha, right? You just set it to that. And then what we just said can be motivated by many reasons, but we'll see it later. But I think I can just write that the next value of W is the previous one plus, well, the slope is f, right? And we want to take a step of width of length h. So the height difference is going to be h times that slope. And the big question is, what is that slope? Well, I mentioned it. It's the slope where you are right now, right? So it's going to be at the current time, which we're going to call ti. And it's going to be at the current solution, which we call wi. This is Euler's method, right? And by the way, these are, of course, ti's here, right? So that's Euler's method. It's not a big surprise for anyone. But we'll analyze it like crazy right now and see what's actually going on here. I can say already it's of course not a method that is used too much because it's not accurate enough, and we'll see what that means. Here it is in the slides, by the way. Or here's first a slide about the grid, saying that you spread out points equally. And of course, we'll come to adaptive. If you think about chapter 4 here, I said at some point, hey, maybe we don't want equal h. And we'll come to that later. But for now, all these steps are equal. Here's a slide deriving Euler's method, and here comes Euler's method. Let's see a way to derive it. Clearly, it can be motivated from Taylor, almost exactly like with Newton's method. We did Taylor and said, look, it's actually not a straight line, but let's pretend it is. For a completely different problem, solving roots, but anyway. So if you look at you're standing at YTA, TI, pretend that's not what we're doing actually, because we're not at the true solution. But at the first step, we are. And then you can make a little, you can make a Taylor expansion here, and you're getting h, or the jump in t, times the derivative. And if that was it, you would be done. That would predict the next value. But of course, it's not it, because it's not a straight line. So there's a quadratic term that we can cut off with this psi. So Euler's method is really just saying, OK, let's pretend it's a straight line, right? And this is not really, we don't really need Taylor for this. We will need this, though, because it tells us exactly what I said before. What is that first error? And it can actually be written as h squared half times the second derivative. And that should make so much sense for you guys now that, first of all, it depends on the second derivative, because we just said it's exact for straight lines, right? It's not exact for a parabola. So it makes sense that it depends on the second derivative. If you run Euler, you get an error, and you make the problem worse, so the second derivative is twice as large, you would expect to make much bigger errors. H squared there might surprise you. I don't know if it does. If I divide h by 2, let's zoom in and look at that. Would you have guessed that the error is going down by, if we just look at one time step from ti to ti plus 1, and pretend we're standing at some true solution? It's not really, right? But pretend we're standing at the true solution there, and you're trying to predict this true solution here. So what you're doing is that you're taking this slope, right? And you're ending up there. And what I just said that this is h squared half times the second derivative of y at some point, right? And what I don't know if you have an intuition about is, what if I do h half? What if I just go there? What is this error? Maybe based on this figure, you can see that it's actually h squared, right? It's a quarter of before. Anyway, Taylor tells us that it is. Does this mean that, just if we're going to go ahead of ourselves, does this mean that this would be a quadratically on order h squared method at the end? Exactly, we did something very similar with composite Simpson, where everybody thought it was h5. And then when we added them up, it was h4. Remember that? We lost an h. Exactly the same thing is going to happen, because sure enough, this is 1/4 of that, right? But I only went halfway. You're going to have to go another step, right? You're going to have to compute a new slope and go there. And that's also going to introduce 1/4 of the error. And adding that up makes it more like half an error. We'll make it more rigorous. But just, it's good to know that this is something we will define very soon to be the local truncation error. At every step, you're making an error of this. But if you bring down h, you're going to have to take more steps. So that will counter that effect a little bit. But anyway, I'm getting ahead of myself. Let's look at the theorem. So it's kind of, as I said, nice that there is a theorem and an error bound and everything. It's not that practical. But using the same conditions as we always do, I'm going to have to tell you to bound the second derivative of the true solution. This is very impractical, like it was for your problems before. How on earth can I bound the second derivative when I'm trying to compute a solution that I don't know what it is? And you know, and when we teach this in the grad courses, there are ways to do it. In practice, though, normally it's enough with an argument saying it can't be too large. Okay? There are physical reasons, but if you actually want a number on it, you're going to do a pendulum in your programming assignment, and there are physical properties that allow you to find a bound on that based on total energies, etc. So it can be done. From numerical analysis point of view, it's really just saying that m is not that important. It's a constant, right? And if it's going to depend like that. But the end result will involve that constant, but at least that constant doesn't depend on your numerical method. And the theorem says the following. Look at this. You see the left-hand side? Can you identify that as being the error at time ti? Because the true solution is y of ti. This is y. And the w's are the numbers you compute, and wi will be the number you compute. So this is, I will often call the error for obvious reasons. We like to put absolute values on it because we don't know if w is above or below. Doesn't matter. And here's a bound. And if you look at it, it looks a little iffy, I guess. Maybe the first thing you should identify here is h. There's only one nice little h. In fact, for many purposes, this entire expression will be replaced by just ordo h. OK? So it is what I said. It's not going to be h squared because of this effect. It's going to be linear. So you run a whole Euler and you divide h by 2, it's roughly going to be twice as accurate. Then you have a bunch of stuff. As I said, if you make m bigger, it's going to be a bigger error. But not that bad, just linearly. OK? You know what's much worse? Look at that L. That's Lipschitz. OK? So in particular, if you try to solve something like the square root from before, it's going to be really bad. But it turns out this connects to that error I mentioned before, that when you go over here, you're not just adding up these h square errors, you're also getting the wrong slopes. And we need Lipschitz to tell us how bad it can be. And we'll see how that L pops in. But you see in particular an exponential dependence. And if you have a feeling for how bad exponential functions are, if you're trying to go far away in time, this bound is completely practically useless because it will just explode. And it's actually correct. There are solutions that will explode, but we're not interested in them. But the bound doesn't know that. So take this bound for what it is. Nobody uses it in practice. I'm sure I assigned problems where you will use it because it's kind of nice that we have it. In practice, it's just going to give you two big bounds usually. It's not practical. What is critical, though, and the beauty about the proof, is that it's really a constant times h. And when I say a constant, I mean something that doesn't depend on h. It depends on, of course, the equation and the Lipschitz constant and the time you're going to, but not h. So it's all really exactly by the definition of ordo. It's bounded by constant times h. That's what we want to do. Let me prove it. It's very short, and not very short, but it's not too difficult either. So what I like about this proof is that it doesn't need much. It needs the problem. We're trying to solve this equation, and we'll call the true solution y. The true solution is always y. We start at alpha, and we're going to go from a to b. And then we have a method that is proposed. It's a discrete equation. It will give a recursion. And we want to make a statement about y ti minus wi and say that it can't be too large. Should be possible, right? So what I mean about that is that it's nice when you have an important proof that doesn't depend on 10 chapters of other proofs before. We will use very little information. We will just use Taylor and solving a recursion equation. So here's what you do. Just for completeness, I'm going to repeat the Taylor in a different language from before. So we start by doing Taylor about point where you're standing. So this will, you take the true solution yt, and about some point ti, you're doing a Taylor, which is telling you that the next one can be written as where you are plus h times the derivative, right? And then you got to cut it off. But we'll go further later on. But I'm going to cut it off. So I haven't really done much. In fact, this size will be different. But you know how we do that. Eventually, we'll just say we don't know xi anyway. But strictly speaking, every time you take a step, it will be a different xi. So we put an I on the xi. All right, just for notation, there are going to be so many parentheses t, function evaluated at parentheses ti. So I don't just define yi to be y of ti. Okay, it's kind of obvious, but when I write yi, y so far has only been a function. Okay, we have numbers ti that are just numbers that you decide on. There are of course going to be numbers wi. And we consistently with those, we define just yi. It's just notation. And I will also allow me to use this horrible notation, prime I, which is y prime at ti. All right, so this looks really iffy because it looks like I'm now differentiating. First I define a number, and then I'm differentiating it. But of course, the way to see it is that you define a function y prime, and you're doing the same trick on that. So just that makes it shorter. The next y is the previous one plus h times the slope, plus an error. And I have no other notation for that. I'm just going to keep the xi. Anyway, this is a critical number that we're going to talk more about later, but we'll come to it very soon. All right, so how do we do it? this is true. Let's just start slowly and say you're standing at the first step. You're right on the true solution, and you want to take one step. What is the error? How do we get our hands on the error? So this is W, right? This is the definition of W. If W is 0, the error is 0. We start exactly at the true solution, right? But I want to look at, let's say, W1, which is W0 plus H of this. And there's a true solution saying that Y of 1 is equal to Y0 plus this, right? What is the error? I think you can almost see that this is the error in that first step. Okay? And the way we get it, how do we get an error? If I have an equation for the true solution, I have an equation for the approximate one, and I want the difference. The error is the difference between the true and the approximate, right? Let's just subtract the equations. It's a standard trick. I'm going to subtract the equations. Subtract, well, Euler's method, right? Or the approximate solution, if you wish. And then you're getting this. yi plus 1 minus wi plus 1 equals, and here you get yi minus wi. So you see, this is kind of nice. This is what we will call the error if we put an absolute sign on it. But you don't have to do that yet. So I'm getting an equation that's telling you the error at the next step, given the error at the first step. But we have to keep on going. We're getting plus h, and then we're getting the jump in f's. So here's going to be f of, well, the first one is actually easy. It's really just yi prime. And we'll do something with that soon. Minus f at ti wi. That's what Euler said that we wanted to do, right? And finally, there's an error term. That was h squared half times this second derivative. All right? Let me do a few more steps here. This looks iffy. I don't know how to treat it, really. But what can we say about yi prime in terms of f? F is the slope. It's really because it's y. It's the true solution. The true solution satisfies the fact that at point I, if you differentiate it, you get f, right? That's not true about your numerical solution, by the way. In fact, there is no derivative of your numerical solution. Your numerical solution is just a bunch of numbers. The only function floating around here is the given f and, of course, the true solution y. Your numerical solution is not a function. It's kind of important to emphasize. There are other methods that do it differently. What I'm trying to say here is that this is really, I'm copying everything else, but this here, yi prime, is really f of ti comma yi, because it's a true solution. So that's just based on the definition of what we're trying to solve. Okay? And then the error term I'm not going to do anything with. So let's just put it here. All right, so is this good? Well, at the very least, I'm telling you, if you give me the error at step I, let's say it's the first step, then that error is 0. I can predict the next error. And I do it by looking at what type of error you're making in f and adding this annoying h squared thing. We can make this much smaller. We're going to do that in following chapters. This, however, is always going to be an issue. All right, what am I doing? It's time to take absolute values and start simplifying it a little bit. We keep the methods there. So the absolute value on everything here, because I want an error, right? So this gives that yi plus 1 minus wi plus 1. At least in my left-hand side, I have what I want. This is what the theorem is talking about. Namely, the error at step at some time. And so I could put an absolute value on everything. But you all remember the triangle inequality, and this is going to be bound anyway. So I'm sure you allow me to do this and just distribute these absolute values as I wish. This is a positive constant, so I can do this. yi minus f of ti comma wi, absolute value. And then we turn this into, well, let's leave it as it is, but I'm going to need to put an absolute value on the second derivative there. Okay? All I did was to take absolute value of both sides, then it would be an equality. But then I say that I really want to distribute the absolute values and add up a bunch of positive numbers. Then it's the triangle inequality saying that now it's just less than or equal to. absolute of a plus b is less than or equal to absolute a plus a absolute of b. All right, what now? Now it's getting better here. If you look at the theorem, I kind of want to stop writing this and just give up and say this is a constant, right? Or it's bounded by a constant. So the first thing I'm going to do is to just replace that by m. And that might be too pessimistic, but it's less than or equal to, OK? So m is a bound on the second derivative. That's not so much the interesting part. Do you see what I need, what condition I need in able to bound this? This is where the connection with Lipschitz come in. You could talk about bounded derivative, you could talk about anything, but exactly the right thing you need is to be able to say that if you make a jump in y, we have a wrong y value. The true solution is yi, and you have an incorrect wi. Then the f's will also be different. And if they are like square root, that they could be hugely different, that's a big problem. But Lipschitz tells us, no, it's just a constant times the difference. So we're going to use those two steps. So Lipschitz will tell us, so first of all, let me just copy that one. Here, Lipschitz tells me that that's less than or equal to that, right? Where L is a Lipschitz constant in the second variable of the function f. And as I said, I don't really want to be dealing with this. It's an error, and I only care about how it depends on h. But let's put it like that. And one last simplification, just saying that this is really just 1 plus HL times the error plus some number that you're adding in. This is very pessimistic because m might be huge somewhere and not somewhere else. And I'm just adding m everywhere. But it's just a bound. So do you like this? If you allow me to introduce error, it's really saying the next error is bounded by the previous error plus h squared m half. And it's multiplied by, sorry. It's bounded by a multiple of the previous error plus some number. That's kind of nice. The only thing left is solving that recursion. And that's not too difficult. We do, I'm not sure you saw that theorem directly, but you could unwind it. But you should be comfortable with the fact that it's actually very similar to a geometric sum. But let me write it in terms of a theorem. They do it a little differently in the book. I prefer to do it this way. Let's just say, so you just want to solve that. Here's a lemma that you might not have seen. If the recursion relation, or let's just call it the recursion for now, an plus 1, I'm changing the notations, we're not. And let's just say alpha is not 1, so we don't have that special case. Has the solution an equals. So you're going to get these alphas n times, multiplying where you start. And then you're going to get a beta. And you're going to get an alpha n, and you'll remember the geometric sum formula there, maybe. That's kind of where it comes. But it's not trivial. But all of you would be able to figure this out if it was an exercise. But let me prove it anyway, because it's so short. All right, so if n is equal to 1, I'm going to do by induction. You don't have to do that. But if n is equal to 1, then a1, according to this formula, is equal to alpha to the 1 times a0 plus beta times alpha minus 1 over alpha minus 1 equals alpha a0 plus beta. Well, that's exactly what it is. So clearly this formula is correct for n is equal to 1. OK? Now suppose it holds for n. And then you try to show that it holds for n plus 1, right? So you're writing down what n plus 1 is. A of n plus 1 equals alpha an plus beta, plus beta, right? We assume it holds for n. So I just replace this by the proposed formula. An alpha a0 plus beta but then I have to add back the beta. And somehow you can see, let me see if I can squeeze it in here. Clearly we're getting the alpha to the n plus 1 A0 that we want. We're getting an extra alpha here, but then we're adding a beta. Is that going to work out? It will. You can write it as beta alpha n plus 1 minus alpha over alpha minus 1. But then you're adding a beta here. And if you multiply this beta by alpha minus 1 divided by alpha minus 1, you can put it together here and cancel out. And I'll just write it here. So I get the end result A0 plus, no, I'll go somewhere else and do that. Sorry about that. We'll go over here. Maybe I should ditch the methods. No, we need them. So anyway, that ends up being alpha to the n plus 1 A0. And then you get a beta, and you're getting an alpha to the n plus 1 minus 1 over alpha minus 1. Because if you give them a common denominator here, you multiply this by alpha minus 1 divided by alpha minus 1, you'll see that you'll be subtracting 1 beta, 1 alpha, and adding 1, 1. Sorry, you'll be adding in the beta. You'll be adding in the alpha. I'll do it. If I'm confused, then I should expect you guys to be confused, or not. Plus beta alpha minus 1 over alpha minus 1. OK? You put these in a common denominator, you'll end up having a beta alpha minus plus a beta alpha. They cancel out. But we'll end up getting a minus beta in the numerator, which is here. All right, that's it. So this is the formula, right? By induction, it holds for all n. All right, anyway, this was all just in order to be able to solve an equation of the form. The next one is a multiple of the previous one plus some number. OK? That's exactly what we have. The next one, well, there's a bounding here. But in order to keep on doing the bound, if I can exactly evaluate the right-hand side, it will still be a bound, right? So it will, at every step, I might make a too pessimistic estimate, but it's a bound for each error. And I might, in worst case, add them all up, right? The error is going on here. So applying this here to this, let me repeat it here. Apply to error is bounded by the previous 1 plus HL, the previous plus h square m half. Then you get, well, you just do it. Here's the solution. So the error is going to be I plus 1. I want to do the I plus 1s, but maybe I shouldn't. No, that's good. Will be bounded by the constant I'm multiplying by. That's 1 plus HL, right? Next error is a constant I'm multiplying the previous error by plus some number. That's the alpha there. So that's going to be to the n plus 1 times what? The initial error. You got to start somewhere, right? Plus, and then you're getting this huge term, which says that you take the beta, the thing you're adding in, the h square m half, and then you're getting the alpha to the power of n. That's the 1 plus HL to the power, and I'm plugging in n plus 1, minus 1 over 1 plus HL minus 1. That's all I did. And we can see what we're trying to get, by the way, before we're trying to simplify. We're not quite there yet. But we're trying to get something that, well, the HM we have, there's an H that we need to lose. We'll see what that comes. But you can actually see already now that these 1s go away. And we're dividing by HL. And we're going to get 1H here, M over 2L. So you can see that we're doing pretty well. It seems that they have replaced this whole thing by some sort of exponential. Why do I think I don't like this? Let's do that step. Let's just do that simplification. It's 1 plus HL to the n plus 1 E0 plus H m over 2l. Then again, we have left this thing. Okay? So let's try to match what they are saying there. Why do you think? First of all, they seem to not have this term at all. Why would you think that is? They just skipped that term. We're going to take this away. Sorry. What is E0? It's the error that in the difference between my numerical solution and the true solution at time t0, right, at time a. Well, you know that. It's alpha, right? It doesn't make sense to not start there. By starting at alpha, y0 minus w0 is equal to alpha minus alpha equals 0. y0 is 0. If it's not, here's the formula. But let's not keep it around. Why don't I like this? Why do I want to rewrite this as an e to the something? There's an h. That's really the fundamental thing. I mean, you can discuss exactly what expressions are good or bad and whatever. I don't want an h here. If it looks like this, I'm not able to say that this is order h, obviously, right? You really need to write that. So constant depending on everything, but not the method, h. So how do you simplify that? Let's see. What are we going to do here? Let's see. Note that, according to our method, E0 is equal to 0. And then 1 plus HL. Well, I want to be able to take it to power. We don't like to take powers of 1. It's like a binomial thing. It's not nice at all. So let's just bound it, since we're bounding things like crazy anyway. In fact, this HL might not be small, but it should. If you have a huge Lipschitz constant, you better bring down h, right? So this is fairly small. So the whole Taylor thing, e to the x, right? That's a usual, a common trick. And the good thing about that is that 1 plus HL to some power. Am I calling it n nowadays? Sorry, I switched here. That's because I had n's over there. Sorry, I'm going to have to fix it. That. I. All right, anyway. Then you can take it to power. And it's bounded by the power here, right? And why is that good? Because it turns out there's an h there multiplied by a number. Can we bound that? And by the way, this number is at most going to be, remember our grid. We're going from A to B in steps of h. And the last solution we're going to compute, we could call Wn, right? But clearly, h times our last solution is always going to be bounded by b minus a, right? In particular, h times I plus 1 is really just equal to time I plus 1, minus a if it's not 0. So this is really equal to e to the l time I minus a. And then we're done. Yep, exactly done. So error, let's replace it by i's, is less than or equal to hm or 2l. We ditched this one, and this one here we replaced by e to the l ti minus a. And there's still a minus 1, which is important. This could be huge, then the minus 1 is not important. But this tells us in particular that if you're not going very far, let's say the special case that ti is equal to a, you're not going anywhere, then the error is 0. So it's kind of nice to have it there. Anyway, I know it's a lot of material, but let's just repeat it. The big thing was to do Taylor and subtract the Taylor to get an equation for y that I have erased, unfortunately. But that equation said that yi plus 1 is equal to yi plus some slope plus a h squared term, right? Subtract Euler's method from that, and you get a recursion equation for this error. Okay? Next key step was being able to bound the jump in f when you have two different y's. And that's Lipschitz. The second derivative, we just say that's less than some number. And we end up with just a simple recursion equation of this form. Okay? It's, even if you hadn't seen that formula before that we had, it's elementary math to solve a recursion equation. And the solution is this geometric series type form that pops out a term dependent on where you start, but you get this type of expression here. And we say A0 is 0 because there is no error when we start. There could be, but normally that would be not so important. And we were not happy here because we cannot really say that it's some big number times h. So therefore, we rewrote it using the exponential, and we get the expression. It's kind of nice. I think I don't know if you appreciate it. I think it's nice. Let's try it. And then you think about whether you have questions about that. I'm not going to give you a yes question.
Sorry, why did you have to transform it to an exponential before you could apply the identity on h?
On which identity? In the numerator or?
No, the 1 plus hl.
To the power of I plus 1?
Yeah.
Yeah, well, how do you want to replace it? How do you want to bound that? By binomial?
Divided by pi minus a, right?
Well, the key that allows me to see that the a goes away is that h will multiply this linearly, right? In some form. So I really want to get bound it or equate it to something that is h times that number, right? And binomial would give you that, really. If you wrote out the a plus b to some power, it would have a lot of terms, and they would be higher order. So you would get it from that as well.
Right, but why couldn't you just say h is equal to pi minus a over I plus 1 or something like that?
Oh, so sure. So h, let's talk about h. H is small, right? It's b minus a divided by n. But then you get an n in this equation. And n is h. N is dependent on h, right? If h shrinks, n increases. I mean, it's a good point, but it's so h here is b minus a over, I would call it n, right? The number of intervals, right? And that's, you can plug it in, and it's small. You might look at it and say that it's small. The problem is that it grows. And we're going to let h go to 0. In fact, if you let h go to 0, n goes to infinity. But it's of course the same thing. I think that the whole trick with the exponential was to bring these together and realize that h really doesn't, you can bound, you cannot bound, well, you can bound h, it's going to 0. You cannot bound n, the number of steps. But you can bound h times I plus 1. That's kind of cool. Anyway, I'm not giving you a function for this because it's so easy. Yeah, more questions. Sorry, I'm right.
Can you go over that last step again?
This here?
Yeah.
The 1 plus HL?
Yeah,
so this bound here is, of course, just Taylor, right? Or whatever definition of E, whatever you want, right? We're taking it to a power. Well, then it's also bounded by this to a power. All the numbers are positive, right? So I'm getting HL times I plus 1. Okay? And now it's time to start thinking. You could leave it at this form, but there's still an H. I don't like the H. I would like to say, the end goal here is to say that you give me a problem. And remember what I mean by a problem. I mean an equation, but I also mean A and B. That's the problem for me. So you tell me what equation you want to solve. That, of course, gives you a number M, an L, and it also gives you A and B. In fact, this TI, you can just put a B, right? I mean, because you're going to the end eventually, right? But I want to remove all references to H to be able to say that it converges. And that's the reason I just said that if you multiply H by a number that is at most n, it really goes back to just this. There is a number n such that H is b minus a n, right? Okay, and that number n is, of course, the largest number I will ever plug in here. I is my iteration number, right? So think about this way. You run it, then you divide H by 2. Then your numbers, you're going to have to go twice as far. And overall, this expression, they cancel out and become just a constant b minus a, right? In fact, H times I minus plus 1 is bounded by the time interval, b minus a. That was why I did that. And of course, if you really want I, you can put ti here. I would be happy to just say it's less than bound again and a b there. We're just bounding things like crazy here. I'm just getting, it's not going to go to infinity as h goes to 0. That's my goal. And the reason is that I've now proven convergence. I haven't defined what convergence is, but you all have a feeling for what it is. I've proven that if you let h go to 0, you will be able to predict the end result with better and better accuracy as h goes to 0. Eventually, it will converge. It might be really, really bad. Eventually, it will converge. Why do I know that? Because it's a big number that won't change when I divide h by 2 many times, right? So that's kind of nice. It's all convergence. But like I said, it's actually completely useless because of that exponential. And we'll see an example. I'm going to run an example in MATLAB without a function, just showing you how to do it. And I'm sure I'm going to do some more interesting things soon, but I'm sure you know which example I'm going to run. Here's my model problem to begin with. Let's go from 0 to 1. And let's start at 1, OK? So in many ways, you could say that you're trying to predict, and what is the true solution? The true solution is e to the t, right? So you could formulate this problem that I'm looking to approximate the true solution. Quite often, you actually ask yourself, what is the true solution at time b, at time 1? So I'm really trying to approximate e here. That's the goal. How do you do it in MATLAB? Let's look at this method. Just some MATLAB techniques here that you might like. I would recommend, just like you did for Simpson and trapezoid, to throw out this grid to begin with. So you might want to do something like, there will be a parameter, number of points you're going to use. Let's say 10. Can you see that? Yeah. And then, of course, h is going to be 1 over n. That's easy. Now, you might want a timeline. And here I start warning you guys again about MATLAB versus math. This is what we in math call ti. And it's a vector of ti's. And now I just call it t. And even worse, ti is actually ti plus 1. You see why? Because MATLAB starts at 1. So t1 is 0. But t2 is what we call t1, t2. We like to start at 0. These are MATLAB issues. Not a big deal. We'll handle it. All right. We need a function f. It's a function of a t and a y. And I want to solve that equation. So it's really just equal to y. That was easy, right? And now I'm going to do one. I want to start somewhere. So w, and I don't think it's a surprise to you. So I know that for Simpson, etc., many of you could get away without using vectors. I think now we want to look at the solution. You don't really have to do it if you just want the end value. But I would strongly recommend putting all these numbers in a vector. Just like I put all the t's in a vector, I want to do that with the same. So if you don't mind, I'm going to start at the starting value, 1. And I'm going to keep on adding things at the next positions. In fact, now comes the one-liner here that solves the problem. We're going to take 10 steps. The equation says that the next one is the previous one plus h times f at the current step. OK? That's it. Isn't that neat? So that's why I'm not giving you an Euler function. You have to do it yourself. We got 10 numbers, actually 11 numbers, right? Because of this MATLAB issue that there's a 0 in the beginning. And you could look at them, but of course we like to plot things. There is the solution. At this point, you should definitely compare with the true solution. So why don't we do t comma x of t? And there's the true solution. Are you impressed? Sometimes it makes sense to put little markers so you see what's going on. And you see that the numerical method took 10 steps, and you can see how they're going there. Yeah. We know a lot now. I mean, we know about this. You might be happy about this. Most people are not. Doing 10 steps and getting that accuracy is kind of bad. But at the very least, what do we know? We know that I'm going to change h, and we know how it's going to scale. And why don't we just focus on the very last error? It seems to be equal to 2.6, like 0.12, right? Or 13. 0.12. If I divide h by 2, where will I end up? Right in between here, hopefully. If I'm in that regime. You never know. This is an asymptotic bound, but let's do it. So this is the reason you should always write scripts for your MATLAB stuff. You should never do what I'm doing. Because now I have to repeat everything and make mistakes all over again. If I put that in a file, I would just go and change n and rerun it, right? So do that. I did not. So I have to redo it, and I have to remember everything I did. I have to create a new t. I have to restart it. I should definitely, in my first version, have put an n there. That's much better, right? But I think that's fine. And now I want to keep the old one, so I'm going to do an hold on here. Let's make this guy red. And we don't need that. All right? And excellent. Here comes this other guy. It took 20 steps. and it seems to be better, and it ends up, but only half better. Twice as much work and twice the accuracy. It's a linear method, order h. It's kind of pathetic, but it works. This is what we do. Of course, in a computer, if you want to kill it, just do 1 million, right? And it will take a fraction of a second. But we're going to develop better methods. We're going to have methods. The one you're going to use in your programming assignment, you will take one step here. It's actually a more complicated step, but you will take one step, and you will kind of visually, you wouldn't see the difference. So that's how good methods we're going to find soon. Let's bound this error as well, just to see an example of our formula. What do we need to do that? We need this, right? So let's just see if we can bound the error at time 1. Error. Well, M is kind of difficult because you need to know the true solution. So as I said, this is really the first piece of why this expression is worthless in practice. But we do know the true solution. And the second derivative is going to be also e to the t, right? So it's bounded by e. So let's set it to e. Lipschitz constant. Do you have a Lipschitz constant for me? For this equation? E is too high. Lipschitz is easier. It's the slope of this function. It's a bound on the slope. Remember, for most functions, there are no issues with kinks and absolute values, right? Lipschitz value is how much will y go away? How much will the function y go away? It's kind of the same thing. If I had two different y's here and plug it into this function, how much will the function go away? It's the identity function. So it's really just 1. It's like f of x is equal to 1. If I put a 2 in front of it, it would be 2. So let's put 1. Now you have everything, but of course you're going to need, why don't we just plug in a b there, right? So we're saying error. And by error, well, let's use the notation. The last error is bounded by h m over 2l times, and as I said, we're usually interested in the last. So why don't you just plug in b minus a here? Okay? So b minus a is 1, l is 1, l is 1, m is e. So I would say this is equal to e minus 1 over 2 e. Yeah, that's a little annoying. H e e minus 1 halves. We'll check it with MATLAB. We don't need a number for it, really. So if we do h, what did we do? First we did h equals to 0.1, right? So 0.1 times x of 1 is the easiest way to do that. 1 minus 1 divided by 2. So it predicts an error of 0.2335. Our error, we looked at it, it was actually 0.12, but that's not too bad. That's similar to stuff we've done before. It's actually less than a factor, or about a factor of 2 away. That's completely unusual, and that's because this function, this simple model problem, is the worst case. If you do simpler things that are more normal, that don't explode, you would get the same error, but error prediction. But at the very least, it does predict that if you divide h by 2, which we did in the next step, right? The error goes down by a factor of 2, of course. That's kind of boring. Let me show you a more interesting function. What did I make up here? Just because e is just too boring. Another example. Y prime equals f equals y times 1 minus 16t. All right? Is this Lipschitz in y? And then you're actually going to have to ask, if I just ask that out of the blue, you're going to have to ask, well, what is the domain? Because if I allow t to be, if I allow all of R2 here, you would have a hard time finding an L to bound these things. But the good news is that t is going to be in a strip. I'm going from, in this case, 0 to 1, I think. Which means that this number never gets larger than 15 in absolute value, right? And it's really the same as before with the Lipschitz constant of 15. So yeah, it's Lipschitz. True solution you found by separation of variables. And it ends up being a constant times e to the t1 minus 8t. All right, let's just run it and see what happens. So you just replace your function by this expression. I'm going to make it a vectorized so we have it in case needed. And you can almost just exactly rerun. I'm going to get, of course, the last time step. I want to erase my plot. And it's, of course, not exp any longer. So let's take that away and replace it by the true function, which is, well, the constant is 1. Sorry. Let's start at 1. OK? What is it? Exp of t times 1 minus 8 times t. All right? This is now with 20 values. You see that visually it's confusing because it gets better. How do you interpret that? Well, it goes to 0. And both of them have the property that they go to 0. So of course, in an absolute sense, it gets better. That doesn't really mean that you're happy about that. Question?
Yeah, for your initial function, you said 15 and 16. Is that going to change?
Oh, what's the 15, you said?
So,
oh, I wrote the wrong number. Oh, look at that. That will change things. Did I recompute it? You see, now really, you should have done a script, right? I don't even know if I recomputed it, but I think I did. I started at 1. Should be fine. All right, we'll see as we refine h. Anyway, yeah, so the fact that it goes to 0 at the end should not make you happy. You already knew that the solution is going to 0. You can argue from all types of reasons that this function will go to 0 by just looking at it, right? So likely, the reason you're doing it is that you want to predict when it's half or something, right? And then it doesn't look so accurate. But of course, you can keep on refining h here. And if you do h, if we do n equals to 40, I'm redoing everything. And then we recompute a solution. Hold on. And we plot. You see that it's getting better. This indicates that I actually now got the 16 right, because it seems to be right in between. And you may or may not think that's worth doing. All right? Are you impressed by Euler's method? You shouldn't be, but you should be impressed by the fact that you can prove something about what it does. I will just quickly start a little bit on next and without finishing it up. You don't have any homework, so I can run behind on it. But we're going to introduce some notation. Let me just connect to what we said before. I mentioned the word local truncation error. This is that h square type thing we had from before. Okay? That's really something very important. It's the error you make in one step, ignoring all this recursion and everything. When we made one step error, it was h square m divided by 2, right? That's really, we need a word for that, because that's what we want to make smaller. In fact, if you think about this entire proof, suppose that the time when I wrote h squared, suppose I can replace that by h cubed. I think you can all see, well, it's actually getting a little complicated because we had h's here as well. But they're actually going to be even smaller. So at the very least, I think I can convince you that that would be able to, we want to increase the power here. Just like we did for Simpson and trapezoid, we don't want an h, we want an h squared. So I think you should be convinced that if I just go back and replace that h squared by an h cubed magically, that would give me an h squared here. Or higher, right? So that's the goal. And the name of that little term is called local truncation error, although it's divided by h. And let me show you the method that actually, it's just one slide telling you how to make it better. Remember that in order to derive Euler, I wrote out Taylor, and I said, let's stop here. OK? So the truncation error became this second derivative term. I'm going to define a new method that adds, remember, this is Taylor. This is where you are plus h times the slope. What is the new method going to do? Plus h squared half times the second derivative. That's a second order Taylor method, and it will be much more accurate. There are some issues in how to compute it, but of course you can do this for any level. So what this is saying, you go up to n, and the remainder will be h to the n plus 1, and that is the Taylor method of order n. Okay? And I could just, well, it can be written down like this. It's really exactly the same method, You start at alpha. You take steps. I replace the whole f here by a big Tn, where the Tn is, of course, f. So a Taylor method of order 1 is Euler. Right? But if you add in one more, you get a new method. You can add in as many as you wish. All right? And just for showing, it's a little deriving these things. It's a little tricky, but for this equation, all I need to do is to add a little term here, namely h squared half times f prime. And that's the only tricky part. What is f prime? Do we know that? It's a little tricky because it's a total derivative with respect to time of a function that depends on time in two ways, right? Clearly, if you know the true solution, you can plug it in, but you don't need to. You can go to your multivariate calculus and say that it's a partial derivative with respect to its first argument times the inner derivative, which is 1, plus a partial derivative with respect to the second argument times, that's just a 1D function, it's just a total derivative, right? A little tricky. This, of course, is equal to, what is y prime? I will use it all over and over. Y prime is f, right? So this is really just f. So this makes it easy to compute this because df dt is minus 16y. And df dy is 1 minus 16t. And then you want to plug on the f itself, which puts a square on that guy and a y there. All right? So it's a little tricky to get these higher order derivatives. If you can do that, you can just define a new function, f prime, which is the time derivative of f. And you write it there. And let's see. There it is, right? And the Taylor method simply adds in h squared half times f prime of ti comma wi. I'm sure I messed it up, but let's look at it. Well, this is exactly the same h. I should have plotted it in a different color. Wait. Did I have the true solution here somewhere? All right, are you impressed by this? It's exactly the same h, and it's right on top of the true solution. This should convince you that actually you don't need n equals 20. This problem is too easy. You should have a smaller, or 40, or whatever, right? So this is a little demo just showing how extremely more accurate this method became, because I added in h squared half of this to that term. Anyway, I'll let you go there. Have a fun spring break, and office hours now, if you want to come.